you're seeing here is a right-angled triangle. And it may be a familiar object to most of you, specifically because you might have studied Pythagoras' theorem at least a few times. Specifically for this one, I'd like to attribute it with these kinds of units, 3, 4, and 5. And those units are special for the sides of a triangle because they're integer units. And we can check that they fit, because 3 squared plus 4 squared is 5 squared. And that's exactly what Pythagoras' theorem tells us about right-angled triangles. Now, that begs the question, 3, 4, 5, that's a nice triangle, that's an easy triangle with integer coordinates. But are there a lot of other ones with integer coordinates? I mean, a lot of times in exercises, we'll often see rational or even irrational units for the side lengths of a triangle. So what if we want to look for integer side lengths? Is there a process to find all of them? So the first thing we're going to want to do is maybe look at the actual equation. And so I'll denote 3 variables. It's an equation in 3 variables, x squared plus y squared is equal to z squared. And we're looking for triplets x, y, z with integer, that are integers. X, y, and z need to be integers. Now, of course, something we might realize is that if a 3, 4, 5 triangle is a right-angled triangle, then also a 6, 8, 10 triangle is going to be a right-angled triangle. And, I mean, you can see that from the equations. If I look at 3 squared plus 4 squared equals 5 squared, well, if I just add some k factor in the front, and in this case I can even square it, and so if I multiply by any square number, or just any integer really, then I'm just going to get another triplet, right? Because I'm multiplying the whole equation by an integer or by some constant, and it doesn't change. And so in this case specifically, I chose to multiply by k squared, because if I multiply by k squared, then really what I have is I've got k times 3 squared, plus k times 4 squared, plus k times 5 squared. So basically what's happening is each of my variables, x, y, and z, have a common divisor of k. So the first thing we're going to be restricting on our equation, because it's kind of boring to just get a solution and multiply it by some constant. I mean, that's pretty easy to do, but we're not interested in that. So what we're going to do is actually we're going to restrict so that x, y, and z don't have any common divisors. That's going to be our first condition. And in particular, that's actually going to restrict so that none of the variables, no 2 of the variables have a common divisor. And we can see that with x and y, for example. Let's say x and y have a common divisor k, right? So x is k times some small x, and y is k times some small y. Well, then you'll see we'll get k squared times x squared plus k squared times y squared is equal to this big z squared. But then that means that k squared, if I factor out the k squared, is going to divide the big z squared. So z itself is going to be some k times a small z. So whenever 2 of these, and we can further this argument for y and z and x and z, so whenever 2 of these variables have a common divisor, then the third one is also going to have a common divisor with the other 2. So that means that we can actually restrict fully that no pairs are going to have a common divisor. So that's the first thing we're going to do with that equation. Now the second thing we're going to do is we're going to consider specifically x and y, and we'll kind of forget about z right now. And we're going to ask, what are 2 types of numbers that we have? We can have even numbers and we can have odd numbers. So we might want to ask, when is x and y even, or when is x and y odd? So let's first look if they can both be even. Well, that's not going to work, right? Because if they're both even, well, they have a common divisor of 2. And we just saw that if 2 of them have a common divisor, then the third one also has a common divisor. So we're not going to worry about the case where x and y are both even, because that will just be the case of multiplying some of our solution by a constant. And so that'll be taken into account for. So that's not happening. Now we can consider a more complicated case of when they're both odd. And at first sight, there might not seem to be a problem with this. But let's see, we've got odd numbers and they're squared. So maybe we want to look at what happens when we square odd numbers. And if I look at this table here, you'll see that 1 squared is 1, 3 squared is 9, 5 squared is 25, and so on. And in particular, you might note, and if you don't, it's fine, but you might note that each of the numbers on the right column are 1 more than a multiple of 4. See, for example, 9 is 8 plus 1, 25 is 24 plus 1, 49 is 48 plus 1, and so on. And even 169 is 168 plus 1, which is also a multiple of 4. So that's our first fact that we wanted to, and we can actually prove that. If I look at 2s plus 1 squared, which in general s, so we've got a general odd number. Well, when I expand this out, I get 4s squared plus 4s plus 1, and so I can factor out the 4 from the s squared plus s to get 4 times some constant plus 1, so it's always going to be a multiple of 4 plus 1. Okay? Now, the reason that's going to cause a problem is that if we now look at the even numbers, when they're squared, well, we'll see that all those are multiple of 4s, right? And so now what we might realize is that if we take any number, because any number is either even or odd, when we square it, it'll either be a multiple of 4, or it'll be one more than a multiple of 4. Thing is, if we look at this x squared and y squared here, each of them are one more than a multiple of 4 because they're odd. So that means that z squared is going to be 2 more than a multiple of 4. But that can't happen, right? Because if z was odd, then it would have to be 1 more than a multiple of 4, and if it was even, it would have to be a multiple of 4. So that tells us that they can't both be odd, because that's just not going to work. And this type of argument has to do with modular arithmetic, and maybe if you'd looked at my number theory videos, you might see another way, in a nicer way notation to express the argument. So it can't happen. And so we realize that both x and y can't have the same parity. They can't both be odd and they can't both be even. So what we're going to say is that one of them is odd and one of them is even. And in particular, just for the sake of generality, we'll say that x is odd and y is even. And, it doesn't really matter which one it is because we can always just reverse the order of x and y to get some other pair. But it doesn't really matter because addition is commutative. So now what we're going to do is we're going to make a very special transformation. And we're going to consider new numbers, small x, which is going to be big X over big Z, and small y is going to be big Y over big Z. Now the reason I'm doing this is, remember, we've specified that x, z, and y have no common divisors. What that means is that this x over z here is in lowest terms. So this uniquely defines a rational number, and specifically a rational number which is in its lowest terms. And so now we've changed our equation into small x squared plus y squared equals 1 squared. And you can see this by just substituting big X over big Z into the small x, and big Y over big Z into the small y, and you'll see that if I multiply through by z squared, then I get the same equation as I had before. Now the reason I've switched to this equation here is because this allows us to get a very special insight on our equation, and it's related to a circle. And the reason it's related to a circle is because x squared plus y squared equals 1 squared is specifically the equation for a circle of radius 1. And this might not surprise you so much if you've seen my trigonometry video, where we've seen how right angled triangles and circles are actually very related. But if you haven't seen that, or if you're just not familiar with that concept, well, this may look pretty surprising, and it's honestly it's a common idea in mathematics to switch between different objects of study, and study one to then go back to studying the other. In this case, we're going to be studying the circle to understand what happens to our equation that has to do with right angled triangles. And this is just a common philosophy in math that you have to get used to, and it's that often the solution to your problem doesn't lie where your problem does. And so you often want to look at different perspectives, and I think this is a nice example of that. So now I want to take a quick detour to conic sections, and what are conic sections? The reason, first of all, that I want to look at conic sections is that the circle itself is a conic section. And we've reduced our problem to finding rational points on our circle. What I mean by a rational point is a point with rational coordinates. Because if we look back at the previous slide, we'll see what x is a rational number in lowest terms and y is a rational number of lowest terms. So if I can find all the rational numbers and just reduce them to their lowest terms on the circle, then I'll get all the integer solutions to my earlier Pythagorean equation. So let's talk a bit about conic sections, because it'll just make the whole thing more general, and technically we don't even need to do this, but I think it's very nice to do this. Conic sections have to do with double cones, like this. And something that you might note that's very interesting is that if you actually plot the equation x squared plus y squared equals z squared on the 3D grapher, you'll get a double cone. So it's kind of interesting to see that, it might be related to a circle, but it's also related to double cones, and circles themselves are related to double cones through this thing called conic sections. So it's quite an interesting parallel to make. So conic sections are basically the type of curves we get by intersecting planes with this double conic here. For example, if I take this vertical plane, I get these two curves like this, right? This in particular is going to be called a hyperbola, and this is what it looks like on a graph, or if this is our y and x axis. So this is one type of hyperbola, and there are many others. For example, I could offset it. It doesn't need to have a center around 0, 0. It could be horizontally aligned instead of vertically aligned, and I could maybe rotate it around. This one in particular has equation y squared minus x squared equals 1. But in general, you can kind of change and put some coefficients under the y and under the x. Alright, so another type of conic section is the ellipse. And you see if I intersect my conic with a plane like this, then I get something that looks like a circle, but it's actually a stretched out circle. And this is an example of an ellipse, again on x and y axis, y and x axis. And this one in particular has equation x squared plus 2y squared equals 1. And so you might see how this is related to circle, because it's like the circle equation, except by adding this sort of factor of 2 on the y, we kind of stretched it about on the x-axis because it takes more of the y to get to that to that 1. So we basically favor this x-coordinate. And so finally, the last type of conic, which you've seen a lot of actually, is the parabola. And it might be surprising to you that that actually has to do with double conics, but it is. And it's, I guess, the most simple type of conic, and this one in particular is described by y squared minus x equals 0. And so in general, you only have one of the y's or the x squared. The other one won't be. And so you'll note, if you looked through the last three equations, that we often had, x squared terms or y squared terms. And that's for a good reason. That's because conic sections have another name, and they're actually just quadratic polynomials, but in two variables. So basically, you have your quadratic polynomials in one variable, ax squared plus bx plus c equals 0, for example, if you want to find the roots. But you can do that with two variables. I have x and y. I can have an x squared term, but I can also have a y squared term. I can have an x times y term. That's of degree 2 because each of those are of degree 1. But I can also have an x term, a y term, and just a constant term here. And so if I put coefficients on each of those, then I get a larger conic section. And this is just the general formula for all conic sections. Now, an interesting thing to note is that in this case, the number of parameters we have is 1, 2, 3, 4, 5, 6, right? 6 parameters seems like a lot, and specifically the reason it seems like a lot is because we got all of our conic sections by considering intersections of planes with double conics. But planes themselves are only described with 4 parameters. So how come we've got 6 parameters for all our conic sections, but only 4 parameters for planes? Well, you'll note that you can actually complete the square on a lot of these terms. I can have x plus some x term plus some constant, and that gets put into one parameter. And I'll have one parameter on the outside and one parameter on the inside, so that's 2, and I can do the same for y, and so I get a total of 4 parameters. And so that fits better with our plane understanding of how things can be. Alright, so now, what does that tell us? Well, conic sections are actually really special in the study of rational points on curves in general because they have a nice solution for finding rational points on them. In particular, we're going to consider that we already have a point on our conic which is rational, so it has rational coordinates. And that's going to be r. R belongs to q squared, where q, are the rationals, and squared just means that we've got 2 coordinates, right? So the way to get all the other rational coordinates on this conic is to use a concept in mathematics that has to do with mapping things to each other. And I guess it's the same idea where in our earlier we looked at our right angle triangle and we kind of mapped all those integer solutions to rational solutions of a circle. In this case, we're going to map rational coordinates of our conic to rational coordinates on a line. And the way we're going to do that is when we're going to first pick some random rational line. And so what a rational line is just a line where its coefficients are all rational. So it's going to be some rational number times x plus some rational number times y equals some rational number, right? That'll be a line in two dimensions. And so what we're going to do is we're going to take this point r, which is rational, and we're going to draw a line through r and through some other points on the conic, okay? And so that'll intersect with our rational line here. And so that's called a projection of the points of our conic onto that line. And the only point that won't be projected is a point where the line is parallel to our rational line here. And one way to get past that is to consider something called the projective plane, where you have a point at infinity, but we're not going to do that here. And we'll just kind of forget about that point or briefly mention it, because it actually resolves quite nicely even without projective geometry. And so what we can actually do here is we'll want to consider multiple things. First of all, let's assume this point P here is a rational number, okay? Well, you've got a rational point. You've got 2 rational points, and you've got a line coming through them. Now, if you consider the equation of a line that goes through 2 rational points, that's going to be y minus the y coordinate of one of the rational points, is equal to the slope between those two rational points times x minus the x coordinates of the same rational point from which I picked the y coordinates. And if you think about that equation, well, it all involves components of one of those rational points, or both rational points, in fact. And it involves only dividing them, or adding them, or multiplying them. So what you're going to get is actually another rational line, because all of the numbers involved will be rational numbers. So that means if r here, we know r is rational, but if p is rational, then this rational line is going to be rational. Well, this line is going to be rational. And that's interesting because if we have a rational line intersecting another rational line, then by a similar logic, when you solve the system of equations that involves both of them, and you can make a general equation for your solutions, that's also going to involve only multiplication or division or subtraction or addition of rational numbers. So that means that the point of intersection is also going to be a rational point. So what that tells us, briefly, is that if p is rational, then q is rational. Okay? And we can also work the other way around. If q is rational, right, and I draw a line through q to r, well then once again this line is going to be rational, and now we've got a rational line intersecting our conic. And now by a more complicated argument, we can also see that p is going to be a rational point, and the reason for that is that if you consider just the x coordinates of those 2 points, for example, well, you'll be solving some linear equation against some quadratic equation, and in the end you'll be solving a quadratic equation. And we know quadratic equations don't always have rational solutions because there's a square root term involved. But the thing is, if we know that one of the solutions of your quadratic equation is the x-coordinate of r, because that intersects with our conic on our line, and we know that has a rational point, well then that means that the discriminants, and well specifically the square root of the discriminants, is going to be itself a rational number. And so that means that because we're using that same value to calculate the x-coordinate of p, then the x-coordinate of p will also be a rational value. And then just plugging in the x-coordinate of p into the line equation, we get a rational number for the y-coordinate of p. So what we've just done is we've made a one-to-one mapping between rational numbers on the conic and rational numbers on the line. So what that means is I can project all my points of the conic onto a line, and I can just find all the rational points on the line, and then using our formulas for projection, which will all be one-to-one and rational, then we'll be able to get all the rational points in our conic. And you really have to appreciate that because you actually can't do that so easily for later curves. For example, the next class of curves after those quadratic curves or conics are cubic curves, or another name for them is elliptic curves. And elliptic curves are a whole lot more complicated, and finding rational points on an elliptic curve is a much, much harder task, and it's still a field of study, really. So we really have to appreciate that conics are that simple. And so here I'm displaying the quadratic equation specifically so that you realize that this square root here, just to say the same argument again, if this one of these numbers on the plus minus is rational, then the other one has to be rational as well, because the values in it don't change, right? It's only the plus and the minus that change. Okay, so with that in mind, and noting that our circle is a conic, specifically an ellipse that's like shrunk down to a circle, we can specifically carry out that process for the circle. So let's start. We've got a circle which is x squared plus y squared equals 1 squared. So let's draw our circle. And so we can add some axes, the x and the y axis. So now I'm going to draw a line, and it doesn't have to be a line with this slope, of course, it can really just be any line. Any line that intersects my circle at another point than this circle on the left, than this point on the left. We know at this point on the left here, it's minus 1, 0, right? And you'll note that that's a rational point, because clearly minus 1 and 0 are rational numbers. And we'll denote this point as x, y. It's just some general point on our circle, right? And finally, one last thing I want to do is characterize the intersection with the y-axis. And we know that's at x equals 0, but we want to give it a y-coordinate of t. And t is unknown for now, okay? It's just t. And you'll note that if we call this angle theta, then the other angle is theta over 2. And you can see that by using a simple geometry theorem for inscribed angles in a circle. So now, what do we have? We've got y squared equals 1 minus x squared. That's due to this equation of the circle. The equation at the top might seem a little less obvious, but it's actually the equation of our line. And we'll note that the slope of our line, right, well this run is 1, and this rise is t, because we denoted as t. So the slope is going to be t. and we know that the line passes through minus 1, 0. So using the point slope, point intercept form of, point slope form of the line, then we get y minus 0 equals t times x minus minus 1. And so in the end we get y equals t times x plus 1, right? That's the equation of our line. So what we're looking is to characterize the intersection of these two. So we've got t squared times x plus 1 squared. If I square this whole equation, it gives me y squared, right? And so that means I can equate it with the equation I have on the bottom. So I get t squared times x plus 1 squared is equal to 1 minus x squared. Alright, I can get a difference of 2 squares on this side. And now I'll note that, well, we already know one of the roots to this equation, right? And that's when x equals minus 1, because we know the line intersects our circle at x equals minus 1. So we don't really have to worry about it, and we can just cancel it. It's the 1 plus x term here, the x plus 1 and 1 plus x. So that we end up with t squared times x plus 1 equals 1 minus x. And so now, just by doing some rearranging, I can get t squared times x plus t squared equals 1 minus x. And then if I group the x terms, and I group the non-x terms, and I do some division, I get x equals 1 minus t squared over 1 plus t squared. Now that's really powerful. We've managed to get x in terms of t here. And what we'll see in a second, is that we can also get y in terms of t. And that's converting from this equation here, which is in terms of x and y, two variables, which is called a Cartesian equation, because it involves the Cartesian coordinates of the points on our curve, to this parametric equation, where we take the coordinates and we give them in terms of some new variable that we can control. And that allows us to nicely define paths, for example, or if we let our parameter range from maybe 0 to 1, we can kind of draw out a path. So let's first get the y. And we'll note that if I can just plug x back into this equation up here, we get y equals t times 1 minus t squared over 1 plus t squared, all over plus 1. Well, yeah, all of that plus 1. And so then if I just multiply by t, I get t minus t cubed plus t, and then that t is going to be t times 1 plus t squared, so I'll have t plus t cubed. The t cubes are going to cancel, and the t are going to add, so we'll get y equals 2t over 1 plus t squared. These formulae are also pretty interesting, and it's also why I've put the angles here. And they're specifically called t formulae for x and y. And if you're familiar with trigonometric functions, then basically, if you consider the tangent of this theta over 2 angle, right, that's actually going to be exactly t. And so then the sine of that same angle is going to be, this y coordinate is going to be 2t over 1 plus t squared, and the cosine is going to be 1 minus t squared over 1 plus t squared. And they're called t formulae for the trigonometric functions. And they allow you to solve integrals by reducing from trigonometric functions to algebra problems, really. So now that we've done this, we've parameterized our circle. What can we do with it? Let's keep our parameters here. Well, let's see. We're looking for rational points on our circle, right? Because if you'll note, what we just did is, if I go back, is we mapped all the points on our circle to points on this line, right? Because we're doing intersections, points on this infinite line, really, because the closer I get to this minus 1 over 0, the farther up the line is going to get. But now, because, but by the same argument we just had with conic sections before, for every rational point on this line, that's going to map to a rational point on our circle. And we can also see that from a formulae, right? So if I have a rational point t in here, all of these values are going to be rational, because it only involves division, addition, and subtraction. And multiplication, of course. So now, if I consider t a rational number, it's going to be p over q. Those are not prime numbers, they're just numbers. And this is in lowest terms, right? Well, then I can plug in p over q into the x, and for example, and multiply by q squared to get q squared minus p squared equals, over q squared plus p squared, is going to be x. And similarly for y, if I plug in the same values, I'll get y equals 2pq over q squared plus p squared. So now we have to go back, at some point, we have to go back to our triangle, because that's what we really want. So let's express little x as big X over z, and little y as big Y over big Z. So then what we've got is we'll have big X over big Z equals q squared minus p squared over q squared plus p squared. And we know that big X over big Z is in lowest terms. We don't specifically know that this one is in lowest terms. So that means that the numerator, the numerator of this one is just going to be a multiple of the lowest terms for the numerator here, and the denominator is going to be similarly that case as well. So if I multiply the numerator of this rational number by some constant lambda, I'll get q squared minus p squared. And by the same constant lambda, I'll also get multiplying the denominator, q squared plus p squared, right? And so that's also going to restrict us so that 2pq is also going to be the numerator of y over z, because that also involves z, times some constant lambda. So what that means is that all these values here we've expressed as a multiple of the actual values we're interested in. And so now what we want to argue is about, what that lambda can be. So we'll specifically know if I add these two equations, and if I subtract these two equations, I've got lambda times x plus z equals 2q squared, and I've got lambda times x minus z equals 2p squared. What that tells us is that lambda divides 2q squared, and that lambda divides 2p squared. Thing is, I argued that q and p, p over q is in lowest terms, which means q and p don't have a common divisor. So let's assume for a second that lambda divides q squared, right? Well, then lambda has to divide q. But if lambda divides q, then it's also going to divide, then q is going to divide p, right? Because lambda divides q here, and we've got lambda in here, and so we've got to have that q and p have a common divisor. Because lambda divides q, but it also divides 2p squared. So what we actually need is for lambda to divide 2. It can't divide q squared, and it can't divide p squared, because then we'd have common terms, right? So it has to divide 2. So what that tells us is that lambda is either 1 or it's 2. And so if we assume that lambda is 2 for a second, well, let's see. We have lambda equals 2. Well, that means that 2x, in this case, because lambda is 2, is q squared minus p squared. But now if you'll remember our tables from earlier, we saw that square numbers, right, are either 1 more than a multiple of 4, or they are a multiple of 4. So if you consider all the scenarios here, things aren't really going to work out, because the 2 can't be even, otherwise this wouldn't be in lowest terms. So one of them is even and one of them is odd, which means in the end I'm either going to have 3 more than a multiple of 4 or 1 more than a multiple of 4. Because this one, for example, could be even and this one could be odd, which would result in 3 more than a multiple of 4. But this one could be odd and this one could be even, which would result in 1 more than a multiple of 4. But obviously those are odd numbers, which means it can't be an even number like we have on the left side. So lambda can't be 2, that just doesn't work. So that means lambda has to be 1. And voila! Look at that. If lambda is 1, then we've just got x equals q squared minus p squared, y equals 2pq, and z equals q squared plus p squared. And so now if we just choose q and p such that they don't have a common divisor, well then we can characterize all of our integer solutions to the Pythagorean theorem. So let's, for example, just pick a pair. Let's take 7 and 4, right? 7 and 4 don't have a common divisor. So we'll say this one's 7 and this one's 4. So you've got 7 squared, that's 49. And you've got 4 squared is 16, right? So that's going to lead us to 49 minus 16. That's going to be 33. So x is 33. Then similarly, here we're going to have 49 times 16. Oh, and that's a big multiplication. And times 2. Well, we can consider 50 times 16. Well, it's going to be 10 times 16 is going to be 160. So 100 times 16 is going to be 1,600. So 50 times 16 is going to be 800. And I can subtract 16 to get 784, right? And then I multiply that by 2. I get 1,400, 1,608 or something. I might be a bit wrong here, so please don't judge me in the comments or anything, but I might have gotten the multiplication wrong. And then here we're going to have 49 squared. Oh, this is going to be 4. Oh, that's why. That's why this was wrong. We chose 7 and 4 originally, so this is going to be 2 times 7 times 4. Of course, that's a little easier. So 7 times 4 is going to be 28, and 2 times 28 is going to be 56. That was a little embarrassing. And then we have 49 plus 16 here. 59 plus 6, that's going to give us 65. So that tells us that a 33, 56, 65 triangle is a Pythagorean triangle. And hopefully that's true, and you can check that. And if it's not, then I've made a calculation mistake somewhere. And yeah, that's going to complete this video. And hopefully you learned, about nice techniques in mathematics, and specifically the techniques of mapping between different objects to understand other objects. And I think the Pythagorean example is a really good one, especially because it's not really new. This is a thing the Greeks did themselves back in the times of Pythagorean and Archimedes. So it's an interesting thing to look at, and something that we should know if we're interested in mathematics. So yeah, see you in the next one.